Okay, so in this video we're going to talk about reactions of amines. The reactions of amines are basically all the same in that the 2 electrons on the nitrogen are going to be donated. If those 2 electrons are donated to a hydrogen, to a protic hydrogen, we say the amine is functioning as a base. We already talked in our last video today about the factors that influence base strength. Today, in the reactions, we're going to talk about 4 reactions where the nitrogen behaves as a nucleophile. So 2 electron donor to an atom other than hydrogen. 3 of those will be carbon, 1 will be another nitrogen. So the first reaction of an amine behaving as a nucleophile comes from chapter 18, which was the condensation reactions of amines with aldehydes and ketones. So aldehyde and ketone plus primary amine under acidic conditions gives you an imine. So we're talking about the carbon-nitrogen double bond. And as you saw in the previous chapter, depending on substituent Y, you get different versions of these carbon-nitrogen double bonded products. So condensation to produce an imine, first step nucleophilic attack, second step acid catalyzed dehydration. So that's one of our reactions of amines. Only 4, that's number 3, which is a condensation reaction. The next reaction, which is reaction number 1 in our summary, is alkylation. So our nitrogen lone pair attacking a carbon displacing a leaving group. So when that substitution occurs, we have an ammonium salt that can get deprotonated by another equivalent of our amine, and in this case we've alkylated our amine, gone from a primary to a secondary amine. In our last video we said that secondary amines are about as basic, therefore about as nucleophilic as primary amines. So we now have a situation where our product or our start material could react with our other reagent, and so you get a combination of all of these different reactions. If you have enough alkylating agent, this alkylation deprotonation can go on and on until all of the positions around the nitrogen have become connected to an alkyl group. So this would be a quaternary ammonium salt or a tetraalkyl ammonium salt. Now if you don't have any hydrogens attached to that positive nitrogen, you cannot deprotonate to get back to a neutral amine. So this has basically been alkylated to its maximum extent. We call that an exhaustive alkylation. There is a use for these exhaustively alkylated species that I'll talk about now. And that use is what's called a Hofmann elimination. So a Hofmann elimination converts an amine into a tetraalkyl ammonium salt, and that positively charged nitrogen functions as a leaving group. And that leaving group can be removed along with a proton to give you an elimination reaction. That's what we're seeing here. But if you look at the details of this elimination, so alkyl or exhaustive alkylation of your amine gives you this good leaving group. When we do our elimination conditions, our product distribution is unusual in that the major product is not the Zaitsev product. We normally said last semester elimination gives you the more alkyl substituted alkene, and that's because it's the most stable. Here, under these Hofmann elimination conditions, the major product is not the most alkyl substituted pi bond. So this is an alternative elimination that you can use to get the other product. We call this the Hofmann product. So that's a general use or application of this exhaustive alkylation. So this exhaustive alkylation can be followed by Hofmann elimination. Hofmann elimination reagents are silver oxide, water, and then heat. So we've done alkylation, which is just nucleophilic substitution. We've done condensation. If we then go back and talk about what will be reaction number 2, that is acylation. So acylation means we're adding on an acyl group. So if you add an acyl group to a nitrogen, you generate this functional group, which is an amide. So this has the advantage that the product is not as nucleophilic as the starting material. So this is sp3 hybridized nitrogen with no resonance. This is a resonance stabilized nitrogen, and therefore this is going to be less basic and less nucleophilic than our starting amine. So this means we're not going to have overreaction complicating things in this case. So acid chloride plus amine gives you an amide. So this is an example of nucleophilic acyl substitution. Nucleophilic acyl substitution, conversion of an amine into an amide. Then the last type of reaction that we're going to talk about for our reactions of amines is diazonium formation. So the summary tells us that a diazonium salt is this functional group where you have carbon connected to 2 nitrogens, and those nitrogens contain a positive charge. Right, so the name tells you di meaning 2, azo meaning nitrogen, ion meaning positive. So this is the diazonium cation. In general, diazonium salts are pretty unstable. You can give them some extra stability if you connect them to an aromatic substituent, and really most of the diazoniums that you will encounter have an aromatic ring directly connected to one of the nitrogens. However, those things are still pretty reactive and are generally stable at 0 degrees or below. That's actually okay because you can conveniently make these things in an ice bath. So the first important reaction is your aromatic amine reacting with sodium nitrite and HCl. So this is your NaNO2HCl reacting with your aromatic amine to give your diazonium salt. So that's summarized here. NaNO2HCl and our aromatic primary amine gives you the diazonium salt. The mechanism is in the notes. Now you might say, what is the point of making something that is so unstable? And the answer is, this diazonium salt can be converted into a wide variety of other functional groups. So this reaction is not for the sake of making the diazonium, it's for the sake of making the diazonium that you can then convert into something else. And the diazonium, if reacted with a variety of other reagents, can then give you an appropriately substituted product. And notice this is now an alternative way of getting substituents onto an aromatic ring. You might say, well, I already know how to do that for some of these, and the answer is yes, this is just a complementary way of doing that. And this brings together one of the longest sequence of reactions that we will do. We said this diazonium and then conversion of diazonium to something else works well for aromatic amines. Now, in our next video, we'll talk about how you make these aromatic amines from nitro compounds. Short answer is it's a reduction, but you know how to make these nitro compounds by nitrating the aromatic itself. So that was one of our standard EAS reactions. So notice that we can put any of these substituent groups onto an aromatic ring by employing this sequence of reactions. So aromatic to nitroaromatic, reduce your nitroaromatic to the aniline, aniline to diazonium, diazonium then to our final product. So this is a sequence of reactions that allows you a complementary or alternative way of making some of these aromatic products. So you'll notice that that's also summarized in then this block. So this is how you make your diazonium, and then this is how you convert your diazonium into these different substituents. So that's then our brief summary of how amines react. Nucleophilic reactions using the lone pair on the nitrogen. We've talked about 4 different electrophiles that the amine reacts with, giving new functional groups, and then some of those functional groups can be employed further, for example, like in a Hofmann elimination, or in the case of a diazonium, you can then convert it into a wide variety of other functional groups.